Hello, my friends, and welcome back to the You Can Do TV channel.
To replace one aging river crossing, New York launched the largest bridge construction project in state history. A bridge that would become the longest in New York State, with a total project cost of about $3.9 billion. But that number only begins to explain the scale of what happened here. The project consumed more than 220 million pounds of American steel, more than 1,000 piles, more than 300,000 cubic yards of concrete, and over 6,000 steel-reinforced concrete deck panels. More than 7,000 people worked on it, logging over 13 million hours. By the time it was done, this was no longer just a bridge job. It was an industrial campaign stretched across 3 miles of river. And that is what makes the Cuomo Bridge more interesting than a normal megaproject. The challenge was never simply to build something large. The challenge was to replace a live crossing without losing the crossing itself. The old Tappan Zee still carried massive daily traffic. The Hudson still had to remain a working river. Environmental controls still had to be respected.
The new crossing had to do more than carry traffic from one bank to the other. Each span would include 4 general traffic lanes, a bus lane, and emergency shoulders. It would be built with the capacity to accommodate future commuter rail between the spans. It would add a shared use path for cyclists and pedestrians. It would also be designed to last for more than 100 years without major maintenance to its critical, non-replaceable components.
The first real engineering decision was not how to build the bridge, it was what kind of bridge should be built at all. The answer was a twin-span cable-stayed crossing, about 3 miles long, making it the longest bridge in New York State. At its center, the main span would be formed by 2 parallel cable-stayed bridges, each with a 1,200-foot main span and 515-foot side spans. The decks would be composite steel and concrete. The towers would be V-shaped reinforced concrete forms rising 419 feet above the river. And the cable system would eventually use 192 stay cables made from roughly 4,900 miles of steel strands. That choice was about far more than appearance. Cable-stayed construction allowed engineers to clear the river efficiently, reduce major obstructions in the navigation channel, and organize the work in controlled stages. Just as important, the twin-span arrangement gave the project a cleaner way to separate traffic, preserve flexibility for future rail, and break a giant crossing into more manageable structural systems. Even at the design level, this bridge was being shaped by the logic of construction. Its final form was inseparable from the sequence that would create it. The most counterintuitive solution came next. If the river was the hardest place to work, then the river should not be the main workshop. The design builder, Tappan Zee Constructors, leaned heavily on modular construction, fabricating large sections of the foundations, roadway, and superstructure on land before bringing them to the Hudson for installation. Some steel sections reached 410 feet in length. That decision quietly changed the whole project. It reduced the number of difficult field operations, it improved quality control, and it converted a one-of-a-kind megaproject into something closer to a repeatable manufacturing process.
Long before the Cuomo Bridge became a line of towers and cables on the horizon, it began as a fight with the riverbed. The most important part of the bridge was the part almost nobody would ever see. Before a single stay cable could be tensioned, before a roadway could cross the Hudson, engineers first had to create a structural base strong enough to carry a 3-mile crossing designed for more than a century of service. That hidden campaign started with more than 1,000 piles driven into the riverbed and continued with some of the heaviest and most precisely choreographed marine foundation work in New York history. At the main span, the foundation system was not generic. It was engineered around enormous loads, deep bearing layers, and the risk environment of a working river. The anchor piers were supported on 24 steel pipe piles, each 6 feet in diameter with 1-inch wall thickness, driven to bedrock or dense glacial till roughly 165 to 225 feet below the underside of the pile cap. The main towers went even further, standing on 64 piles of the same 6-foot diameter, driven roughly 240 to 280 feet below the pile cap. These were not hollow shells left to fend for themselves. The piles were filled with reinforced concrete to depths of about 125 feet below the cap at the anchor piers and 140 feet below the cap at the towers, creating a composite system that could resist not only vertical gravity loads, but also extreme lateral demands from vessel impact and the bridge's cable-stayed geometry. Each pile had a maximum factor geotechnical design compressive strength of about 5,600 kips, while the substructure near the main span was also designed around ship impact demands measured in the range of 9,000 to 23,000 kips. In simple terms, these foundations were not just there to hold the bridge up, they were there to defend it.
That is why even the act of placing the foundations had to be treated as precision engineering rather than brute force marine construction. The project used protective bubble curtains during pile driving to absorb and dissipate acoustic energy in the water, reducing underwater impacts while work proceeded at scale. And when the time came to position the giant prefabricated foundation units, crews used synchronized jacks to lower football field length elements into the Hudson in a controlled sequence. That detail matters. When a component that size is being lowered over water, the problem is not simply weight. It is balance, rate of descent, differential movement, alignment, and the need to keep a huge structural piece behaving like a single obedient body instead of a drifting mass. Even at the bottom of the job, where the public saw almost nothing, the project was already operating like a mechanical system with almost no room for improvisation. Then came the concrete and the substructure, the phase where the invisible skeleton of the crossing began to lock into place. Instead of treating every concrete pour as a land-based delivery problem, the project pushed production onto the river itself. Mobile concrete batch plants supplied the majority of the bridge's concrete directly on the Hudson, turning the waterway into part of the production chain rather than just the obstacle in the middle of it. Over the life of the project, the bridge consumed more than 300,000 cubic yards of concrete. Enough, as the project notes, to build a sidewalk from the bridge all the way to Key West. But the more revealing detail is where that concrete went. Into pile caps, pier elements, tower bases, anchor structures, and the buried mass that would collect, redistribute, and transmit every future load from deck to cable to tower to ground. The pile caps alone show how massive this hidden stage really was. The main span anchor pier pile cap was about 326 feet long, 35 feet wide, and 12 feet thick. The tower pile cap was even larger, about 361 feet long, 60 feet wide, and 14 feet thick. Both were built in 5,000 psi concrete, heavily reinforced, and shaped not only for gravity and stiffness, but also for ship impact, ice effects, drainage, and long-term durability in a harsh river environment. Their leading edges were shaped to reduce ice loading, and their perimeters were faced with ultra-high molecular weight polyethylene sheeting to reduce damage from vessel contact and abrasion.
Then the bridge began to move outward across the river through its approach piers. However dramatic the cable-stayed main span would become, most of the crossing had to be built the slower, steadier way. One support, one span, one placement at a time. The approaches are carried by 41 piers, spaced on average about 350 feet apart. And during peak construction, more than 50 cranes were working across the 3-mile site. This was where the project stopped looking like scattered marine works and started becoming a continuous corridor. Prefabricated structural elements were brought in by barge, lifted into position, and set onto supports in a sequence designed to keep geometry, schedule, and river operations under control.
Then came the towers, the moment the bridge had to rise with precision, not just mass. The main span's 8 reinforced concrete towers, each about 419 feet tall, were built with self-climbing jump forms,
allowing the formwork to climb as each lift of concrete reached strength. The towers lean outward by roughly 5 degrees, a choice that gives the finished bridge its distinctive lightness, but also raises the stakes during construction. On a cable-stayed bridge, tower alignment is not cosmetic. It controls where the stay cables land, how forces flow into the deck, and whether the unfinished structure remains balanced as it grows.
After that, the long approaches began to take shape. The iconic cable-stayed section gets most of the attention, but the bridge is 3 miles long, and most of that length is not hanging dramatically over the water. It is carried through a long sequence of supports and approach structures. The approaches are supported by 41 piers, spaced on average about 350 feet apart. During peak construction, more than 50 cranes dotted the job site. This was the phase when the project stopped looking like isolated marine works and started becoming a corridor. One support, one span, one lifted assembly at a time, the crossing extended outward.
To place the largest elements via larger pieces, the project relied on I-Lift-NY, a super crane with a 328-foot lift arm capable of raising up to 1,900 tons in a single operation. That lifting capacity did not simply make the work more spectacular. The hardest part was not fabricating the biggest pieces, it was setting them down on the river without turning every placement into a delay, a closure, or a risk. That is where the Cuomo Bridge project changed from ordinary bridge construction into heavy lift engineering. Instead of assembling countless smaller components above the Hudson, Tappan Zee constructors fabricated massive bridge sections on land, including steel assemblies measuring up to 410 feet in length, and then moved them to the river for installation in a much smaller number of far heavier operations. That decision completely changed the placement sequence. First, the large bridge elements had to be fabricated and pre-assembled off-site, where geometry, welding quality, and fit-up could be controlled more reliably than over open water. Then the completed sections were transported into position, aligned with the already built substructure, and prepared for lift. Only after that could the project's super crane, I-Lift-NY, take over. The crane could place enormous components that would otherwise have required many smaller lifts, many more temporary connections, and far more time exposed to wind, tide, and navigation conflicts on the Hudson. But a lift of this scale is not just a matter of power. It is a matter of load path, rigging geometry, center of gravity, barge stability, weather windows, river traffic control, and final alignment at the supports. Every larger piece had to arrive in the correct orientation, be held stable during hoisting, and be lowered into place with enough precision that the next stages of deck and superstructure work could continue without correction. That was the real advantage of the system. By making each move larger and more demanding, the project cut down the total number of river operations, reduced the number of field joints, shortened construction by months, and saved millions of dollars. In mega-project terms, this was the key trade: fewer moves, heavier moves, tighter control.
With the giant modules in place, the deck could advance. More than 6,000 steel-reinforced concrete panels formed the road deck. But on a cable-stayed bridge, deck installation is never just laying out roadway. Every new segment changes the unfinished bridge's weight distribution, stiffness, and balance. This is why the sequence matters so much. The structure is not simply growing, it is passing through a series of temporary states, each of which has to remain stable on its own terms. The finished bridge may look calm, but the unfinished bridge had to be carefully managed at every stage of its life. Then came the stay cables. By 2017, nearly 200 stay cables had been installed on the main span. Their role was not only visual, Each cable changed the force path inside the structure. Deck loads began flowing upward into the stays, into the towers, and then down into anchor piers, pile caps, and foundations. This is where the bridge finally became what it had been designed to be from the start, not just a long roadway, but a cable-stayed machine for managing load over water. Then came the traffic shift. The replacement crossing could not simply appear overnight, because the old bridge still had to carry vehicles while its successor was being built. The north span opened first in August 2017, taking two-way traffic. The south span followed in September 2018, after which westbound traffic moved to the north span and eastbound traffic to the south span. This staged opening was not ceremonial. It was the last proof that the project had managed to replace a live crossing without ever severing the crossing itself. And only after that could the old bridge truly disappear. The original Tappan Zee still occupied the river and still constrained the final work, so demolition became part of the build. Large sections were removed by iLift NY. In 2018, the old bridge's 532-foot center span was lowered onto a barge. In 2019, the east anchor span came down by controlled demolition, and the final steel section was removed. In strict engineering terms, the project was not complete when the new bridge stood up. It was complete when the old structure was physically erased from the river and the new one fully took over.
Reinforced soil can hold back highways more efficiently than traditional concrete gravity systems, and mechanically stabilized earth walls make that possible through layered construction and mechanical connections. This retaining approach relies on interaction between materials rather than mass alone. Used widely in highway and bridge projects, this retaining method combines precast concrete panels with compacted backfill and embedded steel tie strips. Each component has a defined structural role within the assembly. The structural strength comes from soil reinforcement interaction, not panel weight alone. Load transfer occurs along the embedded steel elements extending into the fill. Precast panels are set in place like interlocking pieces, aligned along the planned wall face. Panel geometry governs consistent spacing and joint continuity. Connection tabs cast into each section receive steel tie strips that extend horizontally into the retained soil mass. The tie strips function in tension within the reinforced zone. Those tie strips distribute tensile forces deep into the backfill, forming a composite structure with the soil. Approximately 3 feet of stone is typically placed directly behind the wall face to promote drainage and maintain stability. The granular layer reduces hydrostatic buildup along the facing. The remaining tie strip zones are filled in lifts no greater than 8 inches using approved borrow material. Controlled lift thickness maintains uniform density throughout the reinforced volume. Each lift is compacted to roughly 95% of maximum density to ensure load resistance and long-term performance. Compaction testing verifies achieved density at specified intervals. Some panels settle into alignment quickly, while others require adjustment during placement. Minor positional variation can affect cumulative wall geometry. A slight shift during positioning can influence vertical alignment across multiple sections. Temporary bracing holds sections steady while backfill progresses in controlled layers. Bracing remains until sufficient backfill mass stabilizes the facing. The wall rises course by course, each level locked by compacted soil and mechanical reinforcement. Reinforcement length and spacing follow engineered design parameters. There is something satisfying about watching soil and steel combine into a retaining system that supports real highway traffic. Traffic surcharge loads are accounted for in structural calculations. The finished structure stands as a cost-conscious alternative that balances speed of construction with engineered reliability. Design life expectations align with major transportation infrastructure standards. River diversion and high-head penstocks shape a modern hydroelectric dam and power station. Built to harness river power for electricity production, this project combines a high concrete arch dam with an integrated hydroelectric power station. The scale alone places it among the tallest dam structures in its region. Instead of relying on fossil fuels, the facility converts hydraulic head into rotational force inside massive turbines. That shift directly supports long-term grid stability and domestic energy supply. River diversion tunnels redirect natural flow during foundation excavation. Bedrock is exposed and treated to create a stable base for the arch structure. Foundation preparation determines how effectively loads transfer into the canyon walls. Layer by layer, concrete placement advances upward in carefully planned blocks, each section bonded to the next to form a continuous curved barrier. Temperature control systems are embedded within the concrete to manage heat generated during curing. Thermal regulation prevents internal stress accumulation in large pores. Spillways are integrated into the dam body to regulate excess water during peak inflow periods. Downstream protection structures dissipate energy released from controlled discharge. Hydraulic modeling guides the geometry of these flow control elements. Beneath the reservoir level, intake structures channel water through steel-lined penstocks toward the powerhouse. Inside, turbines connect to generators that convert mechanical rotation into electrical output. Each turbine assembly operates under immense water pressure, translated into shaft torque. That pressure is no small matter. The powerhouse anchors the entire system with monitoring equipment, transformers, and grid connection infrastructure. Transmission lines extend outward, carrying produced electricity to distant demand centers. Grid synchronization ensures frequency alignment with national standards. Seeing a project of this magnitude come together reshapes expectations about what civil engineering can accomplish. The completed structure represents coordinated effort across geology, hydraulics, structural engineering, and energy systems. Integrated design reduces long-term operational risk while maximizing generation capacity. 250 meters now stand in solid concrete, pushing this hydroelectric dam body past the previous 249-meter benchmark and setting a new vertical reference in national infrastructure. Crossing that mark isn't symbolic, it changes structural ranking outright. The dam wall has already reached 250 meters, while the final engineered height is fixed at 275 meters. Concrete placement for the dam body has totaled 3,765,000 cubic meters so far. Each layer is poured in planned stages to control heat and internal stress distribution. Body concrete operations were initiated, and successive lifts have continued rising in calculated increments. Hitting the 250-meter level lands with real weight. Wow, that elevation shift is serious. Upon completion, total concrete volume will approach 4 million cubic meters. Installed capacity is designed at 588 megawatts. Installed capacity defines peak simultaneous turbine output under optimal head conditions. Annual generation is projected at 1.888 billion kilowatt hours, contributing approximately 1.5 billion Turkish lira to the national economy. Energy production at this scale directly converts hydraulic head into measurable economic value. Work advances steadily toward the 275-meter crest. 220 tons lifted in one controlled operation. That is the defining moment of installing a new dome using the Liebherr 11,350. A 126-meter boom extends skyward to transfer the 220-ton structure into position, marking the critical phase of expanding the arena roof, measuring 120 meters long and 60 meters wide. The Liebherr 11,350 is configured with its full boom assembly, aligned for maximum reach and stability. The load rises steadily, suspended with deliberate control as taglines guide its orientation. Once aligned above the support frame, operators lower it with gradual corrections until the dome settles into its final seat. The heavier the 250-ton structure, the more measured and restrained the lifting operation must remain. This installation captures the launch of the overpass, executed during a full traffic closure to allow safe placement across the highway corridor. Preparation centers on isolating the roadway section and positioning 3 large cranes around the span. Each crane is calibrated for synchronized lifting, with rigging secured to balance the steel structure before elevation. Coordinated lifting like this leaves no room for guesswork. The span is hoisted steadily, rotated into alignment, and guided laterally until it clears obstacles and lines up with its supports. Seeing 250 tons suspended above an empty highway changes your sense of scale instantly. Gradual lowering follows, with crews monitoring load distribution and structural response until the bridge settles onto its bearings. One controlled descent decides the success of the entire operation. The project, valued at roughly €2 million, delivers a new overpass, built through calculated staging, controlled closure, and disciplined crane coordination. How do engineers replace a single span within a 19-arch bridge without destabilizing the remaining structure along a major intercity railway corridor? The 19-span brick arch structure lacked clearance beneath its third span from the west, preventing safe installation of 25,000-volt overhead line equipment. Work crews first isolated the affected span while maintaining protection for adjacent arches and active tracks. Monitoring instruments and track shielding were installed to guard against movement and debris. Removing one arch without disturbing 19 interconnected spans raised the stakes immediately. Controlled demolition cleared the brick arch section, exposing the gap prepared for replacement. Precast concrete units were delivered in sections and lifted into position to form a modern bridge deck. Alignment checks followed each placement to confirm load transfer across the remaining structure. Old brick giving way to modular concrete felt like history negotiating with new engineering. Once the deck was secured, new parapets were craned into place to prevent public contact with energized equipment. Brick facing was applied to integrate the new elements with the existing arches. Utilities were reinstated and road surfacing completed, finalizing a structure capable of accommodating electrification safely. Upgrading clearance at this location directly supports quieter, cleaner rail operations along the route.
Would you install wood facade slats without exposing a single screw like LERHO rhomboid cladding does? Installation moves forward by fixing the facade connectors first. Wood slats snap into place through an integrated catch. Hidden fastening protects timber and reduces assembly time. The Mastermatic concrete pipe machine can produce structural pipe sections at industrial scale without manual forming. Production moves forward as aggregates, cement, and water enter a controlled batching system. Proportions are calculated digitally before mixing. Accurate batching ensures consistent pipe strength and wall density. The blended concrete transfers directly into the feed hopper of the Mastermatic, eliminating unnecessary handling. Inside the machine, a mold assembly locks into position while reinforcement cages are set in place. Concrete fills the mold under vibration and compaction pressure. Simultaneous vibration and compression remove trapped air and increase structural integrity. The forming head shapes the interior diameter, while the outer mold defines wall thickness. Wow! The speed of consolidation changes the entire pace of pipe production. Once compaction reaches specification, the pipe section lifts vertically from the mold. The green pipe holds its shape immediately after stripping. Immediate demolding increases output without sacrificing dimensional accuracy. Fresh sections transfer onto curing racks for controlled hydration. Curing conditions regulate moisture and temperature to promote uniform strength gain. After reaching target hardness, each pipe undergoes inspection for dimensional tolerance and surface finish. No shortcuts here. Quality checks determine long-term field performance. Automated controls coordinate cycle timing, mold exchange, and material feed. Sensors monitor fill level and vibration duration to maintain repeatable results. Automation reduces manual variability and supports continuous high-volume production. By the end of the cycle, a finished concrete pipe stands ready for storage and shipment. The Mastermatic integrates batching, forming, compaction, and demolding into one streamlined system. High production capacity combines with structural reliability delivering consistent output built on controlled mechanical action and monitored curing performance.
A deep excavation site sets the stage for the tokamak complex at the ITER worksite. Digging reaches nearly 20 meters, as rock blasting clears space for future fusion systems. Joint treatments and reinforcement follow to stabilize the structure. That depth alone already feels serious. Concrete pouring forms the lower base mat before anti-seismic bearings are installed. This isn't just a building, it's groundwork for energy research. Operators and the CAT 385CL excavator coordinate every swing to load extreme mud volumes into a triaxle dump. The excavator positions its tracks for balance, then lowers the bucket into saturated ground, filling it in a single dense scoop. Track placement here directly affects how much force can be applied without sliding or lift. Hydraulic force lifts the mass smoothly, keeping control as the arm swings toward the truck. Mud drops cleanly into the bed, spreading weight across the axles. That bucket looks like it could swallow half the pit in one move. Each dump is aimed to center the load, reducing twist on the truck frame. Operators adjust reach and swing speed to prevent uneven piling. The truck waits as layers build, each pass adding pressure to suspension and tires. Didn't expect that much material to stack so evenly this fast. You can tell when bucket timing and swing arc are dialed in just right. The CAT 385CL repeats the cycle, digging deeper while maintaining a stable stance. As the bed fills, the excavator feathers the final drops to avoid spillover. Feels like controlled power refusing to rush. Those final placements matter more than the early heavy drops. With the last scoop settled, the load sits level, ready for haul-off. This kind of loading keeps turnaround fast, without pushing the truck past safe limits. The sequence shows how machine weight, hydraulic control, and operator timing combine to move extreme volumes efficiently without wasting motion or stressing the equipment beyond design. Scale becomes clear when a supersized clamshell box culvert is installed for the 407 ETR extension in Whitby, Ontario. Supplied by Anchor Concrete, this structure supports drainage demands while fitting into a live highway expansion. That kind of placement leaves no room for guesswork. Preparation defines the early stage as the installation zone is graded and stabilized to accept the culvert's footprint. Lifting plans are coordinated so the clamshell unit can be lowered in a single controlled motion. One slow move here replaces dozens of corrections later. Cranes guide the precast sections into position, aligning the interlocking edges with measured tolerances. The clamshell geometry allows the halves to meet cleanly, forming a rigid channel beneath the roadway. Seeing those edges meet feels oddly final. Once seated, crews verify elevation and alignment before securing joints and ceiling connections. Backfilling follows in layers, distributing load evenly across the culvert walls. That moment when the fill settles tells you the structure is doing its job. This installation highlights why the Anchor Box Culvert earned recognition from the National Precast Concrete Associations for creative precast use. Designed for strength and efficient assembly, it shortens on-site work while maintaining long-term durability. Projects like this quietly reset expectations for infrastructure builds. As surface work resumes above, the culvert disappears from view but not from function. Water management continues unseen, supporting traffic flow on the 407 ETR extension. Hard to ignore how much relies on what never gets noticed.
A bolted steel arch buried in soil can carry highway traffic without a single drop of poured concrete. Delivery trailers arrive with curved plate segments stacked and labeled for sequence. Crews lay out base channels on prepared footings, checking grade and alignment against survey points. If the base is off, the entire arch follows that mistake. The first pair of plates is lifted into position and temporarily braced. Bolts pass through pre-punched holes, loosely tightened to allow slight adjustment. Additional segments follow on both sides, building upward symmetrically. Each new plate changes the balance, so alignment checks happen constantly. Workers move along the curve with impact wrenches, drawing plates together until the seams close firmly. Crown sections complete the upper span, locking the arch geometry into place. At that moment, the structure shifts from flexible assembly to self-supporting shell. Wow, the shape stands on its own. Side backfill begins only after bolt torque values meet specification. Compacted layers of soil are placed evenly along both sides to avoid uneven pressure. Backfill is not just dirt, it becomes part of the structural system. As fill height rises, compaction equipment passes in controlled lifts, stabilizing the arch against lateral movement. Road-based material is then placed above the crown, followed by surface layers that prepare the crossing for vehicles. The result is a buried steel arch, designed to distribute loads efficiently through soil interaction rather than relying on mass alone. Steel and soil working together carry far more than either could alone. A single pull installs 347 meters of 630 millimeters HDPE without digging a trench. The horizontal directional drilling pullback phase connects the prefabricated pipe string to the drill rig through a swivel that prevents torque transfer. That swivel protects the HDPE from twisting stress. Reaming has already enlarged the pilot hole to match the required diameter, creating a continuous path beneath the surface. The pipe string lies fully welded and pressure-checked along the entry side. Rollers support its weight to reduce drag during installation. Once the drill rig applies steady pull force, the assembly advances into the bore. Pull force must stay within calculated limits to avoid overstressing the pipe wall. Drilling fluid circulates through the hole, lubricating the exterior and stabilizing surrounding soil. Progress continues at controlled speed while operators monitor load readings and fluid returns. Wow! Seeing hundreds of meters disappear below ground in one continuous move feels unreal. A single continuous pull eliminates the need for open excavation across the entire alignment. Balanced cantilever bridge construction extends outward in alternating concrete segments above a river valley. Pier shafts rise first, cast in reinforced concrete to anchor the superstructure. Foundation depth determines long-term load stability. Form travelers then advance along each arm, pouring concrete sections in alternating symmetry. Segment balance prevents torsional stress during extension. Pre-stressing tendons are tensioned inside the box girder to lock strength into place. That overhang length is no joke. Seriously bold engineering. Deck closure links both sides, completing structural continuity for bypass traffic.
Traffic pressure doesn't show itself in concrete or asphalt at first, but the Autobahn A9 near Munich carries it every hour of the day. When one full driving direction had to be renewed, the window was tight, and the expectations were unforgiving. 4 kilometers under constant load leaves no room for hesitation. This corridor supports long-distance freight and daily commuter traffic without extended closure options. The surface layers were stripped down in one coordinated push. 10 Wirtgen large milling machines, models W2200 and W250, operated by Cutter from Memmingen, worked across the carriageway. The task involved removing both the wearing course and the asphalt binder layer. Each pass had to match depth and overlap exactly, or the next stage would suffer. Uniform milling depth directly affects how evenly new layers bond across the width of the lane. Milling advanced section by section, clearing material quickly to expose a uniform base. Seeing that much material disappear in such a short time feels unreal, yet nothing about it is rushed. Transport and logistics stayed in lockstep, keeping the milling flow uninterrupted across the site. Haul routes were timed to prevent idle machines during peak removal periods. Once removal was complete, attention shifted to rebuilding the road structure. A total of 19,000 tons of asphalt binder were scheduled for placement. 5 Vogel pavers, including the Super 1900-2 and the Super 3000-2, handled this phase. This is the layer that quietly carries the future traffic load, even though drivers never see it. Binder thickness consistency plays a key role in load distribution over the pavement lifespan. Material supply came through 2 Vogeli MT3000-2 feeders, delivering a steady mix to the pavers. Consistent feed rates allowed the machines to maintain stable paving speed. Any interruption here would echo forward into surface quality. Continuous material transfer helps prevent density variation along the paved stretch. After the binder layer set the foundation, work moved directly to the open porous asphalt surface. The OPA deck required 8,000 tons of material and a different placement approach. 4 Vogel spray pavers advanced in staggered formation, applying binder spray and asphalt in one controlled sequence. That staggered movement keeps coverage continuous without slowing the line. This method supports uniform spray distribution across adjacent passes. Temperature management and joint alignment remained critical through the final meters. It's easy to forget this road must reopen almost immediately under heavy traffic. Crews adjusted spacing and timing on the fly to keep results consistent. Joint positioning was planned to avoid concentrated stress under wheel paths. Within 2 windows of 48 hours, one of Germany's most loaded motorway sections received a renewed surface. No ceremony, no shortcuts. Just coordinated machines turning urgency into structure. The schedule proved that large-scale rehabilitation can succeed under extreme traffic constraints. In this project, Clavecon, India Private Limited demonstrates the installation of clave block, focusing on alignment, bonding, and load transfer rather than speed alone. Blocks arrive pre-cut with consistent dimensions, allowing crews to place units quickly while keeping joints thin and aligned. A dry surface check and layout marking guide the first course so the wall line stays true. That early alignment decides how clean the entire structure will look later. AAC blocks are lifted and positioned with ease, reducing strain while maintaining accuracy. Thin bed mortar is mixed to a uniform consistency and spread evenly using a notched trowel. Each block is pressed into place and gently adjusted to maintain level and vertical alignment. Excess mortar is removed immediately to keep joints clean and consistent. As courses rise, staggered joints distribute load evenly across the wall. Openings for doors and windows are formed by cutting blocks to size, ensuring tight fits around frames. Reinforcement elements are integrated at specified intervals to improve structural stability. This step quietly carries more responsibility than it looks. Service chases for electrical and plumbing lines are created directly in the AAC blocks, reducing the need for heavy tools or secondary layers. Surface preparation follows, leaving walls ready for plaster or finishing without extensive correction. That smooth finish saves more time than most people expect. Throughout the installation, material handling stays organized to avoid interruptions. Waste remains minimal due to precise sizing and on-site adjustments. Seeing walls rise this fast still feels surprising, even after several courses. The method supports faster build cycles while maintaining thermal and acoustic performance. By the final stage, AAC block walls stand straight, lightweight, and ready for the next construction phase. ClaveCon's installation approach highlights how AAC blocks streamline site workflow while delivering reliable wall structures suited for modern building demands. Cracked asphalt that keeps spreading under traffic pressure demands a fix that seals, reinforces, and holds its ground, and that's where the Fast Patch Asphalt Alligator Crack Repair ACR kit comes into play. Instead of heating or complex prep, this cold-applied system relies on a 100% solids polymer composite mixed on-site, ready to handle stressed pavement. The kit is prepared by combining the components until a uniform material forms, creating a repair compound that stays stable without water or solvents. That no-water formula matters more than it sounds when moisture is the enemy of asphalt. Once mixed, Fast Patch ACR is worked directly into alligator cracks, filling interconnected gaps and locking into the damaged surface. The material spreads to bridge weak zones, forming a protective layer that blocks water intrusion and limits future crack growth. You can tell this step decides whether the repair lasts months or years. As it settles, the compound bonds across the fractured pattern instead of just covering the top. Seeing the surface regain continuity feels oddly reassuring without trying to be dramatic. Human decisions and heavy machines move side by side during the rehabilitation of the Belchen Tunnel on Switzerland's A2 corridor. Planning teams align geological data with tunnel boring operations to stabilize an aging structure without interrupting traffic above. Excavation advances section by section as the tunnel boring machine adjusts to varying rock conditions. That balance between data and steel keeps progress predictable. Rock layers are evaluated continuously, guiding support methods and excavation pressure. Reinforcement follows with lining elements installed to secure the tunnel shell and manage long-term loads. Every installed segment feels like locking another piece into place. Drainage systems are integrated to control water ingress and protect the structure over time. Logistics inside the tunnel remain tightly coordinated, ensuring material flow and safe movement for crews. Space is tight, yet nothing seems out of sequence. Quality checks accompany each stage, confirming alignment and structural integrity before work advances. The Belchen Tunnel rehabilitation shows how infrastructure renewal depends on coordination rather than speed alone. Seeing an old tunnel gain a second life hits harder than expected.
Rarely engineered at this scale, Mannix precast line forms 400mm hollow core slabs for Adamstown. Each tightened on long beds before cutting and loading. That weight feels unreal for everyday builds. Feels like force managed with calm control. A dome roof for the 43-meter propane tank is assembled on the floor, using the wide space to align plates and stiffeners before anything moves upward. Crews seal the edges, set temporary supports, and connect air lines that will pressurize the tank. Air is fed in slowly, lifting the 380-ton roof as one unit. That moment the steel starts rising always hits unexpectedly strong. The roof reaches its final level, guided by markers. Wild to imagine all that weight moving on air alone.
Every pass of the Lorem shoulder ballast cleaner reinforces rail support and reduces future maintenance. Mounted on rail wheels, the machine positions its rotating cutter along the ballast shoulder without disturbing the rails. Material is loosened and guided through conveyors separating reusable stone from fines. Clean ballast returns evenly to rebuild support where traffic causes drift. Didn't expect this machine to bite that deep into packed stone. Excess debris is pushed away to protect drainage. Operators adjust depth on the move, keeping output consistent. As the Lorem unit advances, the shoulder regains its profile, improving load distribution and extending track life. Tamping keeps railway sleepers stable as placer and theorem machines compact ballast using non-synchronous constant pressure tamping. Tines enter from above, squeeze ballast evenly, and vibrate at 35 Hz to lock support beneath each sleeper. That uniform pressure protects alignment over time. The motion feels simple, but the result holds heavy traffic steady for daily rail service.